Welcome to Dreaming Minds. I'm glad you are here to calm your day. This is a space where science slows down and curiosity can rest. Tonight, we begin a long and gentle journey. A journey into quantum science and reality. Not to solve reality, not to define it, but to sit quietly beside it. Most days, reality feels solid. The floor feels firm beneath your feet. Time seems to move forward in a steady line. Objects appear where we expect them to be. Cause follows effect. Everything feels reliable. This feeling of reliability is comforting. It allows life to function. It allows routines, plans, and expectations to exist. But physics quietly tells us something different. At the deepest level we have ever explored, reality does not behave the way it appears. Not slightly different, radically different. Quantum science did not emerge from philosophy or imagination. It emerged from careful observation, from experiments repeated over many decades, from measurements that refused to align with classical intuition. In the early 20th century, physicists began to notice something unsettling. When they examined nature at very small scales, the rules changed. Particles did not behave like solid points. Waves did not behave like smooth ripples. Light refused to choose between being one or the other. This was not a mistake. The experiments were checked, then checked again, then repeated across laboratories and generations. The results remained the same. Reality at its smallest scales was not fixed in the way humans expected. It was probabilistic, relational, context-dependent. One of the most important ideas to emerge from quantum science is this: nature does not always define itself until it is measured. This does not mean reality waits for a human mind. It means interaction matters. In physics, observation does not mean watching. It means interacting. It means disturbing a system, even slightly. When a measurement occurs, possibilities narrow, not because the universe makes a decision, but because interaction limits outcomes. This idea alone quietly reshapes how reality is understood. Instead of objects having fixed properties at all times, quantum science suggests that some properties exist as ranges, as tendencies, as probabilities. Only when interaction occurs do these probabilities resolve into specific outcomes. Physicists like Werner Heisenberg describe this as uncertainty, not uncertainty born from ignorance, but uncertainty built into nature itself. This uncertainty is not chaos. It is structure without rigidity. In everyday life, this feels unfamiliar. Humans evolved in a world where uncertainty was dangerous. Certainty meant survival. Predictability meant safety. So the mind naturally resists ideas that soften reality. Yet quantum science does not ask for belief. It asks for acknowledgement. It asks us to accept that reality may be less solid than it feels, and more subtle than intuition allows. Niels Bohr, one of the founders of quantum theory, often emphasized restraint. He reminded physicists that theory does not reveal what reality is. It reveals what can be said about measurements. This distinction is important. Quantum science does not describe an underlying essence. It describes relationships, interactions, outcomes. Reality, in this view, is not a static thing waiting to be discovered. It is a process continuously unfolding. This does not remove meaning from the universe. It changes the texture of meaning. Instead of certainty, there is openness. Instead of rigid objects, there are dynamic patterns. Albert Einstein famously struggled with this view. He accepted the mathematics, but he remained uneasy with the implications. His discomfort reminds us of something important. Even the greatest scientific minds found quantum reality unsettling. Doubt was not weakness, it was honesty. Modern physics continues to test these ideas. Quantum predictions have been confirmed with extraordinary precision, from atomic clocks to semiconductors, from lasers to medical imaging. The technology of modern life quietly depends on quantum behavior. Yet the meaning of quantum reality remains gentle, not definitive. And this is where Dreaming Minds pauses. You do not need to understand equations tonight. You do not need to follow technical details. All that is needed is a simple recognition. Reality may be less rigid than it appears, and certainty may not be its deepest feature. As the night settles in, let this idea soften rather than challenge. You are not required to solve reality. You are only invited to rest beside it. In the next part, we will move deeper. We will explore how probability replaces certainty and why this does not weaken reality, but quietly reshapes it. For now, allow these thoughts to drift, like waves that do not need to choose a direction. In everyday life, certainty feels natural because it allows us to move through the world without hesitation. We expect objects to stay where they are, causes to produce predictable effects, and time to move forward in a stable sequence. This expectation is not philosophical. It is practical. Without it, daily life would be impossible to manage. Classical physics reflected this intuition. For centuries, it described a universe made of solid objects moving through space according to clear rules. If you knew the position and speed of an object, you could calculate where it would be in the future. Reality appeared fully determined, even if humans lacked complete information. Quantum science quietly interrupted this picture. As physicists began studying atoms and smaller structures, they discovered that certainty could no longer be maintained in the same way. At these scales, particles did not have precisely defined positions and speeds at the same time. Instead, they followed probability distributions. This was not because instruments were flawed, but because nature itself behaved differently. Werner Heisenberg formalized this discovery in what became known as the uncertainty principle. The principle does not say that everything is uncertain or unknowable. It states something more specific and more subtle. Certain pairs of properties, such as position and momentum, cannot both be precisely defined at the same time. Increasing precision in one necessarily reduces precision in the other. This was not a limitation of human knowledge. It was a structural feature of reality. For many physicists, this realization was deeply uncomfortable. It challenged the idea that the universe is fully determined at all times. It suggested that at fundamental levels, reality operates within boundaries of possibility rather than fixed outcomes. Importantly, uncertainty in quantum science does not mean randomness without structure. The probabilities involved are not arbitrary. They are mathematically precise and experimentally verified. Quantum theory does not replace certainty with chaos. It replaces absolute certainty with constrained likelihood. This distinction matters. A coin flip is uncertain because we lack control and information. Quantum uncertainty exists even when all available information is known. It is not ignorance. It is nature expressing itself within limits. As experiments confirmed these ideas, physicists were forced to adjust their language. Instead of describing what a particle is doing, they began describing the probability of finding it in a particular state. If a measurement is performed, reality became conditional, dependent on interaction. This shift does not mean that particles are unreal before measurement. It means their properties are not fixed in the classical sense. They exist as potential outcomes governed by mathematical structure. Niels Bohr emphasized that physics does not describe reality as it is, but reality as it can be observed and measured. This statement is often misunderstood. It does not deny an underlying world. It acknowledges the limits of what science can meaningfully claim. Physics, in this view, becomes a discipline of relationships rather than objects. It studies how systems respond to interaction rather than what they are in isolation. This perspective requires intellectual humility. It accepts that complete descriptions may not be available, not because reality is mystical, but because interaction defines what can be known. For the human mind, this can feel unsettling. We are accustomed to thinking of reality as a collection of things with fixed attributes. Quantum science suggests a different picture, where properties emerge through interaction rather than existing independently. Yet this does not weaken reality. It makes it more dynamic. instead of a universe frozen into predefined states. Quantum theory describes a world that continuously unfolds within constraints. Outcomes are not arbitrary, but neither are they fully predetermined. This has practical consequences. Technologies such as semiconductors, lasers, and quantum clocks rely directly on these principles. The probabilistic nature of quantum systems is not a philosophical abstraction. It is a working foundation of modern technology. At the same time, the interpretation of these principles remains open. Different frameworks attempt to explain what quantum probabilities represent. Some focus on knowledge, others on physical processes, others on mathematical structure. What unites them is agreement on the experimental results. This agreement matters more than interpretation. Quantum science demonstrates that nature behaves consistently, even when it defies classical intuition. The universe is not confused. Only human expectations are challenged. As certainty softens, a new form of stability appears. Not the stability of rigid outcomes, but the stability of reliable patterns. Probabilities replace absolutes, yet order remains. For dreaming minds, this distinction is important. The goal is not to dissolve reality into abstraction, but to recognize that reality is more flexible than everyday experience suggests. As night deepens, this flexibility can feel comforting rather than threatening. The need for absolute certainty relaxes. Control becomes less urgent. Questions do not demand immediate answers. Quantum science does not ask us to abandon reason. It invites us to adjust it. In the next part, we will explore how probability is not weakness, but structure, and how reality remains dependable, even when certainty is no longer absolute. When probability enters the description of reality, it is often misunderstood as weakness or lack of knowledge. But in quantum science, probability does not replace structure. It becomes the structure itself. This distinction is essential because it separates everyday uncertainty from the deeper behavior observed in nature at small scales. In classical thinking, probability is usually a temporary tool. It is used when information is missing, when variables are too complex, or when outcomes depend on many uncontrolled factors. In such cases, probability fills the gap until certainty can be restored. Quantum science does not use probability in this way. In quantum theory, probability is not waiting to be resolved by better instruments or more data. It is the final description. Even with perfect experimental control, outcomes are described in terms of likelihood rather than certainty. This is not a failure of theory. It is the conclusion of it. The mathematical framework of quantum mechanics predicts probabilities with extraordinary precision. Experiments confirm these predictions repeatedly across different systems and conditions. What cannot be predicted is the exact outcome of a single event, only the distribution of many events over time. This means reality behaves reliably without being rigid. A quantum system does not choose randomly. It follows strict mathematical rules that govern how probabilities evolve. These rules are so precise that modern technologies depend on them daily, from GPS timing corrections to electronic devices that function only because quantum behavior is stable. The reliability of quantum probability challenges a common assumption, which is that certainty is required for order. Quantum science shows that order can exist without determinism, and structure can exist without fixed outcomes. This idea takes time to settle in the human mind, because everyday experience is built around repeatable objects and predictable sequences. We expect the same input to produce the same result. Quantum systems, however, respond to the same preparation with a range of possible results, each weighted by probability. Importantly, this range is not arbitrary, it is constrained. The probabilities are not equal unless the system allows it. They depend on the system's state, its interactions, and the conditions of measurement. This introduces a subtle shift in how reality is understood. Instead of asking what will happen, quantum science asks what can happen, and with what likelihood. Reality becomes a field of potential outcomes, rather than a single predetermined path. Physicists describe this using wave functions, which encode probabilities, rather than concrete properties. The wave function does not represent a physical wave in space. It represents information about possible outcomes. When a measurement occurs, the probabilities are updated, and one outcome is realized. This process is often called collapse, though the term can be misleading. Nothing dramatic physically collapses. Rather, the description of the system changes because interaction has occurred. Before measurement, multiple outcomes are possible. After measurement, one outcome is known. This does not imply that reality is undecided until a human looks at it. Measurement in physics means any interaction that extracts information, including interactions with the environment. Reality is constantly interacting with itself. Because of this, quantum systems are never isolated in practice. They interact with surrounding particles, fields, and forces. These interactions limit which possibilities remain relevant. Over time, this produces stable patterns that resemble classical behavior at larger scales. This is why everyday objects appear solid and predictable. Quantum probability does not disappear. It becomes averaged out across enormous numbers of interactions. Certainty emerges not because quantum uncertainty vanishes, but because it becomes negligible at human scales. This transition from quantum probability to classical appearance is gradual, not abrupt. It is one of the central topics of modern physics research. The goal is not to eliminate quantum uncertainty, but to understand how stable structures arise from it. For dreaming minds, this transition offers an important insight. Reality does not switch between order and uncertainty. It contains both simultaneously, depending on scale and interaction. Probability, in this sense, is not a flaw in reality. It is a feature that allows flexibility, adaptability, and resilience. A universe that allowed only one outcome for every event would be rigid and fragile. A universe that allows structured probability can respond to change. This perspective also explains why quantum predictions are so dependable. The probabilities themselves are stable. While individual events vary, the overall behavior remains consistent. Nature does not behave unpredictably. It behaves statistically. This statistical reliability is what allows science to function. It allows experiments to be repeated and compared. It allows technology to be built and refined. Probability does not weaken knowledge. It reframes it. As this understanding settles, the need for absolute certainty begins to loosen. Reality does not need to be fixed to be trustworthy. It needs to be consistent. For the mind preparing to rest, this realization can feel grounding. Control does not need to extend to every detail. Outcomes do not need to be fully determined in advance. Stability can exist within openness. In the next part, we will examine how interaction shapes reality itself, and why observation in physics is not about awareness, but about participation. One of the most misunderstood ideas in quantum science is the role of observation. Outside of physics, observation is often associated with awareness, attention, or consciousness. In physics, observation has a very different meaning. It refers to interaction, not awareness, and this distinction is essential for understanding what quantum theory actually claims. When physicists say that a system is observed, they do not mean that a human is watching it. They mean that the system has interacted with something else in a way that allows information to be extracted. This interaction can involve instruments, particles, fields, or the surrounding environment. No awareness is required for this process to occur. This point cannot be overstated. Quantum theory does not assign a special role to the human mind. It does not suggest that reality waits for consciousness to decide what happens. It describes how physical systems change when they interact. At small scales, interaction is unavoidable. Particles constantly influence one another through forces and fields. When a particle interacts with a measuring device, both systems change, information is transferred, and probabilities are updated. This is what measurement means in physics. Before interaction, a quantum system is described by a range of possible outcomes. After interaction, one outcome becomes relevant because it has been registered by another system. This registration does not require intention. It requires coupling. Niels Bohr emphasized this view throughout his work. He argued that physics must describe experimental arrangements as complete wholes, including both the system and the measuring apparatus. According to this perspective, it makes no sense to speak of properties independent of the conditions under which they are measured. This idea challenges everyday intuition. We tend to think of objects as carrying properties with them at all times, regardless of context. Quantum science suggests that some properties are relational. They depend on how a system interacts with its surroundings. This does not imply that reality is subjective. It implies that description is contextual. A temperature reading, for example, does not exist independently of a thermometer. The temperature value emerges through interaction between the system and the measuring device. Quantum properties operate in a similar way, though at a more fundamental level. Because interaction defines outcomes, isolation becomes a special case rather than the norm. Truly isolated systems are rare. Most systems are embedded in environments that continuously interact with them. These interactions limit which possibilities remain relevant over time. This process is known as decoherence. It explains how quantum systems lose their ability to exhibit multiple possibilities simultaneously as they interact with their surroundings. Decoherence does not eliminate quantum behavior. It hides it beneath layers of interaction. Through decoherence, probabilities narrow. Certain outcomes become overwhelmingly likely. At large scales, this creates the appearance of a classical world with definite properties. The underlying quantum structure remains, but its effects are averaged out. This explains why everyday reality feels stable. Chairs do not flicker between positions. Objects remain where they are. Time appears to flow smoothly. These features emerge not because quantum uncertainty disappears, but because interaction suppresses it. Importantly, decoherence does not require observation in any psychological sense. It occurs continuously, even in the absence of life. The environment itself acts as a measuring system, constantly interacting with everything within it. This understanding resolves many apparent paradoxes. It removes the need to invoke consciousness as a special force in physics. It grounds quantum behavior firmly in physical interaction, rather than metaphysical speculation. At the same time, it leaves room for interpretation. Different theoretical frameworks explain these processes in different ways. Some focus on wave functions, others on information flow, others on relational states. What they share is agreement on experimental results. The debates within physics are not about whether quantum effects exist. They are about how best to describe them conceptually. These debates are active, ongoing, and carefully constrained by data. For dreaming minds, this matters because it keeps the discussion grounded. Quantum science becomes a study of how reality responds to interaction, not a story about awareness shaping the universe. The mystery remains, but it is a disciplined mystery. Understanding observation as interaction also changes how certainty is viewed. Outcomes are not revealed because someone looks. They are defined because systems influence one another. Reality is participatory in a physical sense, not a psychological one. This participation does not imply intention or purpose. It implies connection. Everything is connected through interaction, from particles to fields to environments. Reality is not a collection of isolated objects. It is a network of influences continuously shaping outcomes. As night progresses, this perspective can feel calming. The burden of awareness is lifted. The universe does not depend on attention to function. Processes unfold according to structure and interaction, regardless of observation. For the mind preparing to rest, this allows a simple release. Nothing needs to be watched. Nothing needs to be controlled. Interaction happens naturally. In the next part, we will explore how these interactions give rise to the appearance of classical reality, and why the world we experience feels stable, even though its foundations remain probabilistic. For most people, the most difficult part of quantum science is not its mathematics, but its apparent distance from everyday experience. If reality at its foundation is probabilistic and contextual, then why does the world we live in feel solid, predictable, and stable? This question has guided much of modern physics, and its answer does not reject quantum theory. It builds on it. The everyday world is not separate from the quantum world. It is composed of it. What changes is scale, interaction, and number. When quantum systems interact in large quantities, their individual uncertainties combine in ways that produce reliable patterns. Classical reality is not the opposite of quantum reality. It is the large-scale expression of it. Every object around you is made of particles governed by quantum rules. Yet you do not observe quantum uncertainty in a table or a wall. This is because the quantum behavior of trillions upon trillions of particles averages out. The probabilities remain, but their effects become extremely small relative to human perception. This averaging is not random. It follows statistical laws. When many quantum events occur together, their collective behavior becomes predictable, even if individual events are not. This is the same principle that governs large populations, fluid motion, and thermal systems. Stability emerges from numbers. In physics, this transition is studied through the lens of statistical mechanics and decoherence. Decoherence explains how interaction with the environment suppresses observable quantum effects. Statistical mechanics explains how large systems follow regular patterns despite underlying uncertainty. Together, these frameworks show how classical properties arise naturally. Position becomes well-defined. Motion becomes smooth. Objects acquire persistence. These features are not fundamental truths of reality. They are emergent properties. Emergence does not mean illusion. It means that new behaviors appear when systems reach certain levels of complexity. Temperature is an emergent property. No single particle has a temperature. Temperature emerges when many particles interact. In the same way, classical certainty emerges when quantum systems interact extensively. This understanding resolves a long-standing tension. It shows that quantum theory does not undermine the reality of everyday experience. It explains it. The world feels stable because stability is a statistical outcome of countless interactions occurring continuously. Time plays a crucial role in this process. Interactions happen rapidly and repeatedly. Any quantum uncertainty that might momentarily appear is quickly absorbed by the surrounding environment. Information spreads, correlations form, probabilities narrow. As a result, macroscopic objects behave as if they have definite properties at all times. This behavior is not imposed, it arises. Importantly, this emergence does not eliminate quantum structure. It hides it beneath layers of interaction. At smaller scales or under carefully controlled conditions, quantum effects reappear. Experiments with isolated systems can reveal superposition, interference, and entanglement. These effects are not exceptions. They are reminders of the underlying framework. Classical reality, then, is not a separate domain with its own rules. It is a limit case. It is what quantum reality looks like when interactions are dense and environments are complex. This perspective allows both views to coexist without contradiction. The quantum world is not strange because it violates reality. It is strange because it reveals reality before it becomes simplified by scale. For human perception, this simplification is necessary. Our senses evolved to detect stable patterns, not quantum fluctuations. We navigate environments where predictability matters. Survival depends on reliable outcomes, not probabilistic nuance. Because of this, the The brain constructs a version of reality that emphasizes continuity and solidity. This construction is not false. It is adapted. It filters out details that are irrelevant at human scales. Quantum science does not invalidate this perception. It contextualizes it. When physicists say that reality is probabilistic, they are not referring to the world of chairs and buildings. They are referring to the behavior of systems at scales far removed from direct experience. Confusing these levels leads to unnecessary discomfort. Understanding emergence allows the mind to relax. It removes the pressure to reconcile everyday certainty with quantum uncertainty. Both are correct within their domains. This layered view of reality also explains why scientific descriptions change with scale. Different tools are required at different levels. Classical mechanics works because it describes the patterns that matter at large scales. Quantum mechanics works because it describes the patterns that matter at small scales. Neither theory is wrong. Each is appropriate. For dreaming minds, this layered understanding supports a calm perspective. Reality does not collapse into confusion when examined closely. It reveals structure at every level, even if that structure changes form. As the night continues, this realization can feel stabilizing. The world remains dependable. The ground does not disappear beneath uncertainty. Instead, certainty becomes a feature of scale, rather than an absolute requirement. You do not need to hold the entire structure of reality in mind. It functions without effort. Quantum processes unfold, interactions accumulate, and stable patterns emerge naturally. In the next part, we will look more closely at time and how quantum science reshapes our understanding of temporal flow without removing its usefulness in daily life. Time is one of the most familiar elements of experience, yet it is also one of the most difficult concepts to define in physics. In daily life, time feels continuous and directional. Moments follow one another. Causes come before effects. The past feels fixed. The future feels open. And the present feels like a moving boundary between the two. Classical physics treats time as a stable background. It flows uniformly and independently of what happens within it. This assumption works extremely well for most practical purposes. It allows motion to be calculated, processes to be predicted, and systems to be synchronized. Quantum science complicates this picture without fully replacing it. At the quantum level, time does not behave as a simple external parameter in the same way. In many quantum equations, time appears differently from space. It does not have an operator associated with it in the same sense as position or momentum. This asymmetry raises questions about whether time is as fundamental as it appears. Some approaches to quantum theory treat time as an emergent concept rather than a basic one. In these views, time arises from change, interaction, and correlation rather than existing independently. What we call time is a way of organizing sequences of events, rather than a substance flowing on its own. This does not mean that time is unreal. It means that its role depends on scale and description. In quantum systems, processes are often described without reference to a global clock. What matters is how states change relative to one another. Correlations replace absolute timing. Events are ordered through interaction, rather than through an external timeline. At larger scales, where systems involve many interacting parts, a shared sense of time emerges naturally. Clocks become meaningful because processes stabilize. Regular cycles appear. Synchronization becomes possible. Once again, emergence plays a central role. Time as we experience it is not contradicted by quantum science. It is explained as a macroscopic structure that arises from countless interactions occurring in sequence. The direction of time, often called the arrow of time, is linked to entropy and the statistical behavior of large systems, rather than to quantum laws themselves. Quantum equations are largely time-symmetric. They do not distinguish between past and future. The asymmetry we experience comes from how information spreads and how systems evolve towards states of higher entropy. This process is not driven by quantum uncertainty alone. It is driven by the accumulation of interactions. This distinction matters because it separates the experience of time from its mathematical description. Physics does not deny the flow of time. It explains why flow appears at certain scales and not others. For the human mind, this explanation can feel grounding. Time does not disappear when examined closely. It becomes contextual. It belongs to the level of description where it is useful. In daily life, time organizes action and memory. It allows learning, planning, and coordination. Quantum science does not challenge these functions. It simply shows that time is not the same kind of entity at all levels of reality. Some physicists explore the idea that time may be relational, meaning that it is defined by changes between systems rather than by a universal clock. In this view, time is a measure of difference rather than duration. It counts transformations rather than moments. This perspective aligns with experimental practice. Clocks measure regular processes. They do not access time directly. They compare cycles. Time is inferred through repetition and stability. At quantum scales, where systems may not exhibit stable cycles, time loses its usual meaning. Descriptions shift toward transitions and probabilities, rather than durations. Despite this, quantum science does not remove the usefulness of time at human scales. It clarifies its origin. It shows that time emerges from order, rather than imposing order from outside. This understanding also reshapes how the present moment is viewed. The present is not a universal slice of reality, shared by all systems. It is a local construct, defined by interaction and information exchange. Different systems may not agree on what counts as simultaneous. This does not affect everyday experience. It affects how reality is modeled at fundamental levels. For dreaming minds, this distinction allows time to be approached gently. The night often changes how time is felt. Minutes stretch, awareness softens. The urgency of schedules fades. This shift is not an illusion. It reflects how attention and interaction influence temporal experience. Quantum science does not explain consciousness or perception. It does not need to. It shows that time is flexible in description, which leaves room for different experiences of duration without contradiction. As this idea settles, the pressure to track time precisely begins to ease. Time continues to function. Clocks continue to count. But the need to hold on to each moment relaxes. Reality does not require constant monitoring. Processes unfold according to structure and interaction. Time emerges where it is needed and recedes where it is not. In the next part, we will explore how entanglement connects systems across space and why this connection challenges classical ideas of separation without violating physical limits. One of the most distinctive features of quantum science is entanglement, a phenomenon that challenges classical ideas about separation while remaining firmly grounded in experimental evidence. Entanglement occurs when two or more systems interact in such a way that their properties can no longer be described independently, even when they are separated by large distances. In classical thinking, objects are defined by their own attributes. Once separated, they carry those attributes with them. Interaction may influence them temporarily, but afterward each object resumes its independent existence. Quantum science introduces a different possibility. Some systems once correlated remain linked in how their outcomes are described. Entanglement does not mean that objects communicate instantly or exchange signals faster than light. It means that their properties are correlated in a way that cannot be explained by classical models of independent states. When one system is measured, the description of the other system is updated accordingly, regardless of distance. This update does not transmit information. It reflects a shared structure established through prior interaction. Albert Einstein referred to this phenomenon as unsettling. because it seemed to challenge the idea of locality, the principle that objects are influenced only by their immediate surroundings. His concern was not philosophical. It was rooted in the foundations of physics. He worried that entanglement implied hidden mechanisms not yet understood. Subsequent experiments addressed these concerns directly. Tests designed to rule out hidden classical explanations repeatedly confirmed the predictions of quantum theory. The correlations observed in entangled systems exceeded what any local classical model could produce. These results did not violate the speed of light or causality. They respected all known physical limits. What they challenged was the assumption that systems can always be described independently once separated. In quantum science, the state of a system can include information about its relationship to other systems. This relational aspect becomes essential rather than optional. Entanglement reveals that separation in space does not always imply separation in description. Two systems can be distant, yet share a single mathematical representation. Their outcomes are linked because they are part of the same overall structure. This does not mean that reality is unified in a mystical sense. It means that interaction can produce correlations that persist beyond direct contact. The universe remembers relationships. These correlations are fragile. Interaction with the environment quickly reduces entanglement. This is why entanglement is difficult to maintain in practical systems. It requires isolation and careful control. At large scales, entanglement effects are typically suppressed by decoherence. Nevertheless, entanglement is not rare at small scales. It is a natural consequence of interaction. Whenever particles interact, correlations form. In many cases, these correlations are classical. In some cases, they are quantum. The difference lies in how the correlations behave. Quantum correlations cannot be reduced to independent properties, plus shared randomness. They reflect a deeper connection in the structure of the system. From a practical perspective, entanglement has become a resource. It is used in quantum computing, secure communication, and precision measurement. These applications do not rely on interpretation. They rely on consistent experimental behavior. The existence of entanglement does not imply that everything is connected in a vague or universal way. It implies that some systems are connected in specific, measurable ways as a result of interaction. This specificity matters. Quantum science does not dissolve distinctions. It defines them carefully. Entanglement has precise conditions, measurable limits, and clear consequences. For the human mind, entanglement can feel counterintuitive because it resists simple visualization. We are accustomed to thinking in terms of objects with boundaries. Entanglement suggests that some boundaries are contextual rather than absolute. This does not undermine individuality or separation at human scales. It explains why separation appears reliable. At large scales, interactions with the environment rapidly destroy quantum correlations. Classical independence emerges naturally. Once again, scale determines behavior. At small scales, entanglement reveals that systems cannot always be decomposed into independent parts. At large scales, independence becomes an excellent approximation. Both descriptions are valid within their domains. Understanding this layered structure helps resolve confusion. Entanglement does not contradict everyday experience. It explains why everyday experience works as it does. For dreaming minds, entanglement can be approached without drama. It does not suggest hidden forces or unseen communication. It shows that reality retains memory of interaction in subtle ways. Connection, in physics, is not emotional or intentional. It is structural. It arises from shared history and interaction. Once established, it shapes possible outcomes. As night continues, this perspective can feel steady. Separation remains meaningful. Boundaries function, yet beneath them lies a quieter structure that records how systems have interacted. Nothing needs to be unified. Nothing needs to be dissolved. Reality accommodates both connection and distinction, depending on scale. In the next part, we will examine how information plays a central role in modern physics, and why some physicists now describe reality in terms of information flow rather than objects alone. In recent decades, many physicists have begun to describe reality using a concept that once belonged mainly to communication theory and computer science. That concept is information. This shift does not replace particles, fields, or forces. It reframes how these elements are understood and connected. Information in physics does not mean meaning or knowledge. It does not refer to thoughts, symbols, or messages in the everyday sense. It refers to the structure of possible states and how those states can change through interaction. In this view, physical systems are described by the information they carry about their own possible configurations. When systems interact, information is exchanged, redistributed, or constrained. This process does not require awareness or intention. It follows physical law. Quantum theory naturally supports this perspective. The wave function itself can be understood as an information structure. It encodes what can be known about a system's potential outcomes. Measurement updates this information. Interaction reshapes it. This approach helps clarify long-standing puzzles. Instead of asking what a particle is doing when it is not measured, physicists ask what information is available about its possible behavior. The focus shifts from hidden states to accessible structure. One reason information has become central is that it behaves like a conserved quantity in many contexts. In quantum mechanics, information is not easily destroyed. It can be transformed, dispersed, or entangled, but it follows strict constraints. This insight has deep implications. For example, black hole physics raised a serious problem. Classical descriptions suggested that information falling into a black hole could be lost forever. Quantum theory strongly resists this idea. Many physicists now believe that information is preserved, even in extreme conditions, though its form may change dramatically. This belief is not philosophical preference. It arises from the mathematical consistency of quantum theory. If information were truly destroyed, the theory would lose predictive coherence. Preserving information maintains structure. In laboratory systems, information flow is directly observable. Quantum computing relies on controlling how information is encoded and transformed in quantum states. Quantum communication relies on maintaining correlations that carry information securely. These technologies treat information as a physical resource. Importantly, information in physics is not abstract. It requires physical systems to exist. Information cannot float freely. It must be encoded in particles, fields, or states. This grounding prevents information from becoming mystical. When physicists say that reality may be described in terms of information, they are not suggesting that the universe is a computer in a literal sense. They are pointing out that physical laws constrain how states can change and how those changes can be tracked. This perspective also clarifies the role of measurement. Measurement does not create reality. It updates information. It restricts the range of possibilities based on interaction. Reality continues to exist, regardless of what is known, but description depends on available information. The emphasis on information also bridges different areas of physics. Thermodynamics, quantum mechanics, and relativity all involve information flow in different ways. Entropy, for example, can be understood as a measure of how information about a system's microstates is distributed. As entropy increases, information becomes more dispersed. Order gives way to statistical regularity. This process defines the arrow of time at macroscopic scales. Once again, information connects fundamental behavior to everyday experience. This does not mean that information is more fundamental than matter or energy. It means that information provides a unifying language. It allows different phenomena to be described using shared principles. For the human mind, this shift can feel abstract, but it does not need to be mentally demanding. Information here is not something to grasp conceptually. It is something that quietly organizes how reality behaves. A system with more available information has more constrained behavior. A system with less information appears more random. These are not judgments, they are descriptions of structure. From this viewpoint, uncertainty becomes manageable. It is not ignorance in the usual sense. It is a reflection of how information is distributed and limited by physical law. This understanding also removes the temptation to overinterpret quantum ideas. Information is not consciousness. It does not imply intention. It does not require awareness. It is a physical descriptor. By keeping this boundary clear, quantum science remains grounded. Mystery remains, but it is disciplined mystery, constrained by experiment and consistency. For dreaming minds, the idea of information can be approached calmly. Reality does not need to be imagined as fragmented or unstable. Information provides continuity across scales. It links quantum behavior to classical experience without reducing one to the other. As the night continues, attention can soften without losing clarity. Systems exchange information continuously. Outcomes unfold according to structure. Nothing needs to be watched or managed. Information flows whether or not it is noticed. Reality organizes itself through interaction. Understanding this allows the mind to rest without needing to resolve every question. In the next part, we will examine how limits on information shape what can be known, and why uncertainty remains even in the presence of precise laws. As physics began to describe reality in terms of probabilities and information, an important realization followed. Even with precise laws and advanced instruments, there are fundamental limits to what can be known at the same time. These limits are not temporary gaps waiting to be filled. They are part of the structure of reality, as described by modern physics. In classical science, limits to knowledge were often practical. Measurements were imprecise. Instruments were imperfect. With better tools, knowledge could improve. Quantum science introduced a different kind of limit. Some constraints remain even when measurement is ideal. The uncertainty principle is one example, but it is not the only one. It illustrates a broader idea that complete knowledge of all aspects of a system is not always possible, not because reality is hidden, but because certain descriptions exclude one another. Knowing a system's position precisely limits what can be known about its momentum. Knowing its energy precisely limits what can be known about how long that energy is defined. These trade-offs are not flaws. They are built into how nature behaves. This means that knowledge in physics is contextual. What can be known depends on how a system is prepared, how it is measured, and which questions are asked. Asking one question restricts the answers to others. This does not weaken science, it refines it. By acknowledging limits, physics avoids false certainty. It replaces the idea of complete description with the idea of appropriate description. A model is judged not by whether it captures everything, but by whether it captures what is relevant for a given situation. This approach has proven remarkably effective. Quantum theory makes extraordinarily accurate predictions precisely because it respects these limits. It does not attempt to describe what cannot be consistently described. Importantly, limits of knowledge do not imply that reality is unknowable. They imply that knowledge must be framed carefully. There is a difference between what exists and what can be simultaneously described. In everyday language, this distinction often disappears. People assume that if something exists, it should be fully knowable. Quantum science suggests otherwise. Some aspects of reality exist without being jointly accessible in a single description. This idea can feel counterintuitive, but it is not unique to quantum physics. Even in classical systems, trade-offs appear. Measuring temperature precisely can disturb a system. Observing behavior can alter outcomes. Quantum limits are sharper, but the principle is familiar. The key difference is that quantum limits persist even when disturbance is minimized. They are not artifacts of interference. They are expressions of structure. As physics advanced, These limits became tools rather than obstacles. By understanding what cannot be known simultaneously, physicists learned how to design experiments that extract the most useful information. Constraints guide inquiry rather than block it. This perspective also clarifies debates about realism. Some interpretations of quantum theory emphasize that limits of knowledge reflect limits of description rather than limits of existence. Reality does not vanish beyond measurement. Description simply becomes incomplete. Other interpretations explore whether reality itself is defined by information. While opinions differ, there is broad agreement on one point. Any successful description must respect the limits imposed by experiment. This agreement matters more than philosophical differences. Physics progresses by refining what can be said reliably, not by asserting what cannot be tested. For the human mind, limits of knowledge can be unsettling because they challenge the desire for completeness. There is comfort in believing that with enough effort, everything can be known. Quantum science suggests a more restrained view. This restraint is not defeat, it is balance. Knowing where knowledge ends allows attention to rest. It prevents endless pursuit of certainty where none is available. It encourages focus on what is meaningful and accessible. In this way, limits of knowledge support clarity rather than confusion. They define boundaries within which understanding can deepen without becoming rigid. For dreaming minds, this idea aligns naturally with rest. The mind does not need to grasp every detail. It does not need to resolve every question. Some limits are not problems to be solved. They are features to be acknowledged. Reality continues to function regardless of how much is known. Processes unfold according to structure. Interactions occur. Outcomes arise within constraints. Understanding that knowledge has limits does not reduce trust in reality. It refines trust. It shifts reliance from complete certainty to consistent behavior. As the night progresses, this perspective can feel settling. Questions remain open without urgency. Uncertainty exists without threat. Knowledge becomes sufficient rather than total. In the next part, we will explore how these limits influence the idea of causality and why cause and effect remain reliable even when certainty is softened at fundamental levels. Causality is one of the strongest intuitions humans have about reality. We expect causes to produce effects in a clear order. We expect events to follow one another in a reliable sequence. This expectation is deeply embedded in how we reason, plan, and remember. Without it, the world would feel incoherent. Classical physics reinforced this intuition. It described a universe in which every effect had a definite cause, and where knowing the present state of a system allowed its future to be predicted. Causality and determinism appeared closely linked. If causes were known precisely, effects could be calculated precisely. Quantum science separates these ideas. In quantum theory, causality remains intact, but determinism is softened. Causes still constrain effects, but they do not uniquely determine them. Instead, causes define a range of possible outcomes, each with a specific likelihood. The connection between cause and effect becomes probabilistic rather than absolute. This distinction is subtle but important. Quantum events are not uncaused. They are not spontaneous in the sense of having no structure. They occur within well-defined physical laws. What changes is that those laws do not single out one inevitable result. For example, the decay of an unstable particle does not happen at a predictable moment. There is no hidden clock counting down, yet the probability of decay over time is precisely known. The cause, the unstable configuration, defines the statistical behavior, even though the exact timing varies. This pattern appears throughout quantum physics. Interactions constrain outcomes. Laws govern distributions, but individual events retain variability. Causality shapes possibilities, rather than enforcing single paths. This view preserves coherence, while removing rigidity. It also resolves a common misunderstanding. Quantum uncertainty does not mean that anything can happen at any time. Outcomes are constrained by physical law. Some events are allowed, others are forbidden. Probability does not imply freedom from structure. The relationship between cause and effect remains reliable at large scales, because probabilities accumulate. When many quantum events combine, their statistical behavior produces stable trends. Classical causality emerges from quantum causality through repetition and scale. In this way, quantum science does not undermine everyday reasoning. It explains why everyday reasoning works. CL feels predictable because the probability distributions governing its behavior are narrow and consistent at human scales. This also explains why causality appears directional. CL fundamental equations may be time symmetric. The accumulation of interactions and the spread of information create effective arrows. Causes precede effects because information flows in that direction within complex systems. Quantum theory respects this structure. It does not allow effects to appear without causes. It does not permit outcomes that violate conservation laws or physical constraints. It only relaxes the idea that causes dictate unique results. Some interpretations of quantum mechanics explore deeper explanations for this behavior. Others accept the probabilistic structure as fundamental. Despite these differences, experimental predictions remain the same. Il faut consiste trace as pire. For human understanding, this preservation matters. It means that reality remains dependable, even when certainty is softened. Actions still have consequences. Preparation still influences outcomes. Knowledge still guides behavior. What changes is the expectation of control. Quantum science suggests that control operates within limits. We can shape likelihoods, but not guarantee specifics. We can influence distributions, but not force individual events. This is not weakness. It is realism. In many areas of life, this model already applies. Weather forecasts predict probabilities, not exact conditions. Medical treatments improve chances, not certainties. Economic policies influence trends, not individual decisions. Quantum causality aligns with these experiences. Recognizing this alignment can be calming. It shows that the quantum view of reality is not alien to daily life. It formalizes patterns that already exist in complex systems. For dreaming minds, this understanding allows causality to remain present without pressure. Events unfold according to structure. Effort matters, but outcomes do not need to be perfectly controlled. The mind can rest knowing that reality is neither chaotic nor rigid. It is structured and flexible at the same time. As the night continues, this balance can feel stabilizing. Causes still matter, effects still follow. The world remains intelligible. Though certainty simply becomes contextual rather than absolute. In the next part, we will explore how different interpretations of quantum theory attempt to describe these features, and why physics allows multiple perspectives without losing coherence. As quantum science matured, physicists reached an unusual situation. They agreed strongly on the mathematics and the experimental predictions, yet they differed on how to interpret what those results mean. This situation is uncommon in classical physics, where interpretation and prediction often align more closely. In quantum theory, multiple interpretations coexist. Each attempts to explain how probabilistic outcomes, measurement, and reality itself should be understood. Importantly, these interpretations do not change experimental results. They change the conceptual story told about those results. This distinction is essential. Physics advances through prediction and verification. Interpretation provides context, not new outcomes. One well-known interpretation emphasizes that quantum theory describes knowledge rather than reality itself. In this view, the wave function represents information about possible measurement outcomes, not a physical object. Measurement updates that information, and probabilities reflect limits on what can be known simultaneously. Another interpretation suggests that all possible outcomes occur, each in its own branch of reality. According to this perspective, the apparent randomness of outcomes reflects which branch is experienced, not a collapse of possibilities. The mathematics remains unchanged, only the narrative differs. Other interpretations focus on relationships between systems rather than absolute states. In these frameworks, properties exist only relative to other systems. There is no single, universal description of reality, only consistent descriptions across interactions. Despite their differences, these interpretations share important features. They respect experimental data. They preserve causality. They obey physical constraints. None of them introduces new observable effects beyond those already confirmed. This coexistence of interpretations reveals something important about quantum science. It shows that physics can be precise without being metaphysically rigid. Multiple conceptual frameworks can describe the same structure as long as they remain consistent with observation. For some, this plurality feels unsettling. There is a desire for a single definitive picture of reality. Quantum science suggests that such a picture may not be necessary. Understanding can be layered rather than singular. This does not mean that reality is subjective or arbitrary. It means that the language used to describe reality can vary depending on emphasis and perspective. Different interpretations highlight different aspects of the same underlying structure. Physics allows this flexibility because it is grounded in constraint. Mathematical consistency and experimental agreement limit how far interpretation can go. Speculation must remain tethered to data. In practice, physicists choose interpretations based on usefulness rather than truth claims. An interpretation may be favored because it simplifies calculations, clarifies concepts, or aligns with other theories. This pragmatic approach reflects the discipline's focus on reliability rather than metaphysical certainty. Importantly, no interpretation assigns a special role to human belief or intention in shaping physical outcomes. Even interpretations that discuss observation do so in physical terms. Consciousness remains outside the formal structure of quantum theory. This boundary protects science from drifting into unfalsifiable claims. It ensures that explanations remain testable and grounded. For the broader understanding of reality, this situation has subtle implications. It suggests that reality can be approached from multiple angles without contradiction. No single description needs to exhaust all meaning. This idea is not unique to quantum science. In other areas of physics, different models describe the same phenomena under different conditions. Fluid dynamics and molecular theory describe liquids at different scales. Both are valid within their domains. Quantum interpretations function in a similar way. They provide different lenses for understanding the same mathematical framework. None of them replaces the framework itself. For dreaming minds, this multiplicity can be approached calmly. There is no need to choose a single interpretation or resolve all debates. The existence of multiple perspectives does not weaken understanding, it enriches it. The mind often seeks closure. Quantum science suggests patience instead. Some questions remain open because they exceed current descriptive tools, not because reality is incoherent. This patience aligns well with rest. The pressure to settle every question eases. Understanding becomes sufficient rather than complete. Reality continues to function regardless of interpretation. Experiments produce consistent results. Technology works. Predictions hold. Interpretation adds meaning without altering structure. As the night deepens, this can feel reassuring. Reality does not depend on agreement about its ultimate nature. It behaves reliably across descriptions. You do not need to decide what interpretation is correct. Physics itself has not decided. What matters is recognizing that consistent structure exists beneath conceptual diversity. In the next part, we will explore how these ideas influence our understanding of measurement itself, and why measurement in quantum science is not a single moment, but a process unfolding over time. In everyday language, measurement sounds like a single moment. A value is read, a result appears, and the process seems complete. In quantum science, measurement is not treated as an instant. It is understood as a process that unfolds through interaction over time. This distinction matters because many misunderstandings arise from imagining measurement as a sudden event. Quantum theory does not describe reality changing because a switch is flipped or a number is recorded. It describes how systems evolve when they interact in ways that allow information to be extracted. Before measurement, a quantum system is described by a range of possible outcomes. During interaction, the system becomes correlated with the measuring device and the environment. After interaction, certain outcomes become effectively fixed because information has spread and stabilized. This stabilization does not occur at a single point in time. It develops as correlations build, and decoherence suppresses alternative possibilities. Measurement, in this sense, is gradual rather than abrupt. Understanding measurement as a process helps clarify why quantum effects are rarely observed in everyday objects. Large systems interact with their environments constantly. Information spreads quickly. Correlations lock in outcomes long before human awareness becomes involved. This view removes unnecessary drama from measurement. There is no special moment when reality suddenly decides what it will be. There is a continuous flow of interaction, leading to increasingly definite behavior. Physicists model this process using open systems theory. In this framework, no system is perfectly isolated. Every measurement involves coupling to an environment. The environment acts as a sink for information, reinforcing certain outcomes while suppressing others. This reinforcement explains why measurement results appear stable and repeatable. Once information about an outcome has spread widely, reversing it becomes practically impossible. Alternatives are not destroyed, but they become inaccessible. This does not mean that quantum theory denies the existence of definite outcomes. It explains how definiteness arises. Outcomes are not imposed by observation. They emerge through interaction and information flow. This perspective also explains why different measurement setups produce different results. Measurement does not reveal pre-existing properties independent of context. It creates correlations that define which properties become relevant. This does not imply that measurement creates reality from nothing. It means that properties are not absolute in isolation. They are relational. They depend on how systems are coupled. In practice, this understanding guides experimental design. Physicists carefully control interactions to isolate specific effects. By shaping how systems interact with measuring devices, they determine which aspects of behavior become visible. This control does not eliminate uncertainty, it channels it. Measurement extracts information while respecting quantum limits. Precision increases in some variables at the expense of others. Measurement as a process also clarifies why repetition matters. A single outcome reveals little. Patterns emerge through repeated interaction. Statistics build structure. Reliability arises from accumulation rather than singular events. This is why quantum predictions are tested statistically. Individual measurements vary. Distributions remain stable. Reality expresses itself through consistency over time, rather than through single moments. For the human mind, this view can feel calming. There is no sudden point at which everything changes. Processes unfold gradually. Stability builds through interaction, rather than appearing abruptly. This aligns with many everyday experiences. Learning is a process. Adaptation is a process. Understanding grows through repetition and reinforcement. Measurement reflects this broader pattern. Quantum science, in this sense, mirrors life, rather than opposing it. It shows that definiteness is earned through interaction, not granted instantly. For dreaming minds, this framing supports rest. Nothing needs to be captured at once. Awareness does not need to be sharp. Processes continue without supervision. Reality does not require attention to become stable. It stabilizes through interaction, whether or not it is noticed. As night continues, this understanding allows the mind to release urgency. There is no need to observe closely. Outcomes will settle naturally. In the next part, we will explore how scale influences description, and why the same system can appear different depending on how closely it is examined. One of the most important lessons of modern physics is that description depends on scale. The same system can appear simple or complex, stable or uncertain, depending on how closely it is examined, and which features are relevant at that level. This does not mean that reality changes. It means that description adapts. In everyday life, scale is rarely questioned. Objects are large enough to be seen. Processes are slow enough to be tracked. Causes and effects unfold within ranges that human perception can follow. At this scale, classical descriptions work extremely well. Quantum science becomes necessary only when scale shifts. When systems are small enough, isolated enough, or fast enough, classical assumptions begin to fail. Properties that seemed fixed become variable. Trajectories become distributions. Outcomes become probabilistic. This shift does not indicate a breakdown of reality. It indicates a breakdown of a particular description. Physics handles this by using different frameworks for different scales. Classical mechanics describes motion at human scales. Statistical mechanics describes large collections of particles. Quantum mechanics describes behavior at small scales. Relativity describes extreme speeds and gravitational effects. Each framework is internally consistent. Each is supported by experiment within its domain. None of them is universally applicable without modification. This layered approach prevents confusion. It acknowledges that no single description captures all aspects of reality equally well. Instead, descriptions are tools chosen for relevance and accuracy at specific scales. Scale also influences which questions make sense. Asking about the exact position of a particle inside a solid object is not meaningful at human scales. Asking about the temperature of a single particle is not meaningful at quantum scales. Meaning arises when questions match scale. This principle extends beyond physics. In biology, cells behave differently from tissues. In economics, individuals behave differently from markets. In each case, new patterns emerge at larger scales that are not obvious at smaller ones. Quantum science fits naturally into this pattern. It does not replace classical descriptions. It complements them by addressing regimes where classical assumptions no longer hold. Understanding this relationship removes the sense of conflict between quantum reality and everyday experience. The table does not flicker because quantum effects are averaged out. The planet follows a stable orbit because countless interactions smooth out uncertainty. The clock ticks regularly because underlying processes synchronize. At smaller scales, where averaging does not occur, different behavior appears. Interference becomes visible. Entanglement becomes measurable. Probability replaces certainty. These effects are not hidden. They are simply scale-dependent. This dependence also explains why quantum experiments require careful isolation. To observe quantum behavior, interactions with the environment must be minimized. Without isolation, decoherence quickly suppresses quantum effects, and classical patterns dominate. Isolation is not artificial. It reveals behavior that is normally overwhelmed by interaction. By controlling scale and interaction, physicists access different layers of reality. This access does not imply that one layer is more real than another. Each layer reflects genuine structure. Classical stability is real. Quantum probability is real. They coexist without contradiction. Problems arise only when descriptions are mixed improperly. Applying quantum concepts to macroscopic behavior without accounting for scale leads to confusion. Applying classical intuition to microscopic behavior leads to misunderstanding. Physics progresses by respecting these boundaries. Scale also shapes intuition. Humans evolved to function at a narrow range of scales. Our senses and cognitive habits reflect this. We are comfortable with solidity, continuity, and determinism because these features dominate at human scales. Quantum science challenges intuition, not because it is wrong, but because it operates outside this familiar range. Recognizing this reduces discomfort. The mind is not failing to understand reality. It is encountering a regime it was not adapted to navigate. This recognition allows a calmer relationship with quantum ideas. They do not need to be internalized intuitively. They need to be acknowledged as accurate descriptions at appropriate scales. For dreaming minds, this perspective encourages balance. Reality is not unstable. It is layered. Stability and uncertainty coexist in different regimes without conflict. As night deepens, scale becomes less important experientially. Attention softens. Boundaries blur slightly. This does not reflect quantum behavior directly. It reflects the mind's changing engagement with detail. Physics remains precise regardless of attention. Descriptions remain valid within their domains. The universe does not require observation to maintain its structure. Understanding scale allows the mind to release unnecessary tension. There is no need to reconcile every description into one image. Different pictures serve different purposes. In the next part, we will explore how these layered descriptions influence the concept of reality itself, and why modern physics treats reality as something that can be described without being fully captured in a single model. When physics speaks about reality, it does not do so in the same way philosophy or everyday language does. In daily speech, reality is often treated as a single solid thing that exists independently of description. It is assumed to be fully formed, fully present, and fully determinate. Physics approaches reality more carefully. In modern physics, reality is defined operationally. This means it is described through what can be measured, predicted, and consistently related through physical law. Reality is not denied. It is constrained by what can be meaningfully said about it. This approach does not reduce reality to measurement. It recognizes that any description requires interaction. Without interaction, there is no way to distinguish one possibility from another. Description becomes undefined, not because reality disappears, but because access is limited. Quantum science sharpens this perspective. It shows that some aspects of reality do not have fixed values, independent of context. This does not imply that reality is incomplete. It implies that completeness depends on how questions are posed. When physicists say that a property is not well defined before measurement, they are not claiming that nothing exists. They are claiming that certain distinctions do not apply until interaction makes them relevant. This is a subtle but important shift. Reality is not a list of properties waiting to be revealed. It is a structured field of potential outcomes shaped by interaction. This view avoids two extremes. It avoids naive realism, which assumes that all properties exist fully and independently at all times. It also avoids radical idealism, which suggests that reality depends on perception or belief. Quantum science occupies a careful middle ground. Reality exists. It behaves according to law, but description is relational. This relational approach appears in many areas of physics. Space and time are described relative to frames of reference. Energy and momentum are conserved within interactions. Information is defined through states and correlations. Nothing floats freely, independent of context. The success of this approach is practical rather than philosophical. It produces accurate predictions. It supports reliable technology. It allows experiments to be designed and interpreted consistently. Because of this success, physics remains cautious about claims that exceed operational grounding. When questions cannot be connected to measurement or prediction, They are set aside rather than answered speculatively. This caution is not a limitation. It is a discipline. Quantum theory does not claim to explain why reality exists. It explains how reality behaves when examined under specific conditions. This distinction preserves clarity. In many discussions, confusion arises when scientific and philosophical meanings of reality are mixed. People may ask whether reality exists when unobserved, or whether consciousness creates the universe. These questions often dissolve when terms are clarified. Physics does not say that observation creates reality. It says that observation defines outcomes within a framework of interaction. Reality does not wait. It responds. This response is consistent and law-governed. Systems evolve according to equations. Probabilities follow structure. Interactions produce correlations. None of this depends on awareness. Understanding this helps keep quantum science grounded. Mystery remains, but it is bounded. The unknown is not limitless. It is structured. For the human mind, this approach can feel both humbling and stabilizing. It removes the burden of needing a final picture of everything. It allows reality to be approached through layers of description without requiring ultimate closure. Reality in physics is not something to be captured in a single image. It is something to be navigated through models that work where they apply. These models do not compete to replace one another. They cooperate. Each reveals aspects that matter at particular scales and conditions. This cooperation is often overlooked. People may focus on apparent contradictions between quantum and classical views. In practice, these views complement each other. One explains stability, the other explains variability. For dreaming minds, this layered concept of reality supports calm reflection. Reality does not need to be reduced to a simple answer. It functions without needing to be fully summarized. As the night continues, the idea of reality as structured potential can feel easing. Nothing needs to be forced into certainty. Description can remain partial without being false. The world remains dependable. Patterns persist. Interaction shapes outcomes. Reality unfolds according to structure rather than intention. Understanding this does not require effort. It requires acceptance of limits. Acceptance that some questions are answered by behavior rather than by definition. In the next part, we will explore how these ideas influence the way physicists think about objectivity, and why objectivity remains possible, even when descriptions are contextual. When physics speaks about reality, it does not do so in the same way philosophy or everyday language does. In daily speech, reality is often treated as a single solid thing that exists independently of description. It is assumed to be fully formed, fully present, and fully determinate. Physics approaches reality more carefully. In modern physics, reality is defined operationally. This means it is described through what can be measured, predicted, and consistently related through physical law. Reality is not denied. It is constrained by what can be meaningfully said about it. This approach does not reduce reality to measurement. It recognizes that any description requires interaction. Without interaction, there is no way to distinguish one possibility from another. Description becomes undefined, not because reality disappears, but because access is limited. Quantum science sharpens this perspective. It shows that some aspects of reality do not have fixed values independent of context. This does not imply that reality is incomplete. It implies that completeness depends on how questions are posed. When physicists say that a property is not well defined before measurement, they are not claiming that nothing exists. They are claiming that certain distinctions do not apply until interaction makes them relevant. This is a subtle but important shift. Reality is not a list of properties waiting to be revealed. It is a structured field of potential outcomes shaped by interaction. This view avoids two extremes. It avoids naive realism, which assumes that all properties exist fully and independently at all times. It also avoids radical idealism, which suggests that reality depends on perception or belief. Quantum science occupies a careful middle ground. Reality exists, it behaves according to law, but description is relational. This relational approach appears in many areas of physics. Space and time are described relative to frames of reference. Energy and momentum are conserved within interactions. Information is defined through states and correlations. Nothing floats freely, independent of context. The success of this approach is practical rather than philosophical. It produces accurate predictions. It supports reliable technology. It allows experiments to be designed and interpreted consistently. Because of this success, physics remains cautious about claims that exceed operational grounding. When questions cannot be connected to measurement or prediction, they are set aside rather than answered speculatively. This caution is not a limitation. It is a discipline. Quantum theory does not claim to explain why reality exists. It explains how reality behaves when examined under specific conditions. This distinction preserves clarity. In many discussions, confusion arises when scientific and philosophical meanings of reality are mixed. People may ask whether reality exists when unobserved, or whether consciousness creates the universe. These questions often dissolve when terms are clarified. Physics does not say that observation creates reality. It says that observation defines outcomes within a framework of interaction. Reality does not wait. It responds. This response is consistent and law-governed. Systems evolve according to equations. Probabilities follow structure. Interactions produce correlations. None of this depends on awareness. Understanding this helps keep quantum science grounded. Mystery remains, but it is bounded. The unknown is not limitless. It is structured. For the human mind, this approach can feel both humbling and stabilizing. It removes the burden of needing a final picture of everything. It allows reality to be approached through layers of description without requiring ultimate closure. Reality, in physics, is not something to be captured in a single image. It is something to be navigated through models that work where they apply. These models do not compete to replace one another. They cooperate. Each reveals aspects that matter at particular scales and conditions. This cooperation is often overlooked. People may focus on apparent contradictions between quantum and classical views. In practice, these views complement each other. One explains stability, the other explains variability. For dreaming minds, this layered concept of reality supports calm reflection. Reality does not need to be reduced to a simple answer. It functions without needing to be fully summarized. As the night continues, the idea of reality as structured potential can feel easing. Nothing needs to be forced into certainty. Description can remain partial without being false. The world remains dependable. Patterns persist. Interaction shapes outcomes. Reality unfolds according to structure rather than intention. Understanding this does not require effort. It requires acceptance of limits. Acceptance that some questions are answered by behavior rather than by definition. In the next part, we will explore how these ideas influence the way physicists think about objectivity, and why objectivity remains possible, even when descriptions are contextual. Uncertainty often carries a negative meaning in everyday language. It suggests lack of control, incomplete knowledge, or risk. In science, uncertainty has a more precise and constructive role. It marks the boundaries within which reliable statements can be made, and it protects knowledge from false certainty. Quantum science places uncertainty at the center of its framework, but it does so in a disciplined way. Uncertainty does not imply that predictions are unreliable. It specifies the form that reliability takes. Instead of predicting single outcomes with absolute precision, quantum theory predicts distributions that remain stable across repeated experiments. This stability is not accidental. It arises from strict mathematical structure and extensive experimental confirmation. When physicists calculate probabilities, they do not guess. They follow equations that have been tested across a wide range of conditions. The uncertainty lies in individual outcomes, not in the overall pattern. This distinction matters because it preserves trust in scientific knowledge. A theory that predicts exact outcomes but fails frequently would be unreliable. A theory that predicts distributions accurately, even when individual events vary, can be extraordinarily dependable. Many areas of science already operate in this way. In chemistry, reaction rates are predicted statistically. In biology, populations are described through averages and trends. In meteorology, forecasts express likelihood rather than certainty. Quantum science formalizes this approach at a fundamental level. By accepting uncertainty, physics avoids overreach. It does not claim more precision than reality allows. This restraint strengthens its conclusions rather than weakening them. When predictions fall within expected ranges, confidence increases. Uncertainty also guides experimental design. Knowing which quantities cannot be simultaneously defined helps physicists choose what to measure and how to measure it. Constraints become tools. Limits shape inquiry. This practical role of uncertainty is often overlooked. It is not merely a philosophical statement about what cannot be known. It is an operational guide for what can be known reliably. Reliability, in this context, means consistency under repetition. If a result appears again and again within predicted bounds, it is reliable, even if it is not exact. Precision is not the same as reliability. Quantum science demonstrates this clearly. Technologies built on quantum principles work because probabilities behave predictably. Semiconductors, lasers, and atomic clocks rely on statistical regularity. Their function depends on uncertainty being constrained, not eliminated. This relationship between uncertainty and reliability challenges a common assumption that certainty is required for control. Quantum systems are controlled precisely by shaping probabilities, rather than by fixing outcomes. Engineers design conditions that favor desired behaviors without demanding exact repetition. This approach mirrors many aspects of human experience. Learning does not produce identical results each time. Practice improves likelihood, not guarantee. Preparation influences outcomes without determining them fully. Quantum science aligns with these patterns rather than contradicting them. From a conceptual perspective, uncertainty also prevents rigid interpretations. It keeps descriptions flexible and adaptable. When new evidence appears, models can be refined without collapsing. Uncertainty allows growth. This flexibility is visible in the history of physics. Theories evolve, approximations improve, domains of applicability expand. Uncertainty marks where change is possible without undermining what already works. For the human mind, this can feel reassuring. Knowledge does not need to be perfect to be trustworthy. It needs to be consistent and honest about its limits. Uncertainty becomes a sign of integrity rather than weakness. In daily life, discomfort with uncertainty often arises from the desire for closure. The expectation that questions must have definitive answers can create tension. Quantum science suggests a different posture. Some questions are answered best by ranges rather than points. This posture does not invite confusion. It invites steadiness. When expectations are aligned with structure, frustration decreases. Outcomes are evaluated within appropriate bounds. For dreaming minds, this understanding supports rest. The mind does not need to chase certainty late into the night. It can accept that reliability does not require finality. Patterns persist even when details vary. Uncertainty also introduces resilience. Systems that tolerate variation are less fragile than those that demand exactness. Quantum descriptions reflect this resilience. They accommodate change without losing coherence. This resilience is visible across scales. Biological systems adapt through variability. Social systems function through tolerance of difference. Physical systems remain stable through statistical balance. Uncertainty supports continuity. As night continues, this perspective can feel calming. The world does not demand exact prediction to function. It operates within ranges that remain dependable. You do not need to resolve every detail to trust reality. Trust emerges from repeated consistency, not from absolute precision. In the next part, we will explore how these ideas influence the way physicists think about completeness, and why completeness in science does not mean having all answers at once. In many areas of human thought, completeness is associated with closure. A system is considered complete when no questions remain unanswered and no gaps are visible. Classical physics once seemed to move toward this ideal. With enough information, it appeared possible to describe the universe fully and predict its future with precision. Quantum science reshaped this expectation. Instead of promising final answers, modern physics emphasizes completeness of framework rather than completeness of detail. A theory is considered complete when it accounts for all observable phenomena within its domain and provides consistent rules for prediction, even if it does not specify every individual outcome. This shift is subtle but profound. It separates completeness from finality. Quantum theory is complete in the sense that it provides a full set of principles governing how systems behave and how probabilities evolve. It does not leave observable phenomena unexplained within its scope. Yet it does not aim to specify every event in advance. Variability is not a flaw. It is part of the structure. This understanding emerged clearly in debates about whether quantum mechanics was incomplete. Some early critics believed that hidden variables might restore determinism and provide a more complete picture. Over time, experimental tests constrained these possibilities. The results suggested that any completion restoring classical certainty would conflict with observed behavior. The conclusion was not that reality is deficient, but that classical expectations of completeness were too narrow. Completeness in quantum science means having a consistent, self-contained framework that accurately describes all accessible phenomena. It does not mean removing uncertainty or context. It means incorporating them properly. This approach aligns with how scientific theories function in practice. No theory claims to describe everything about the universe. Each theory has a domain where it applies reliably. Within that domain, completeness refers to adequacy, not exhaustion. For example, thermodynamics is complete within its scope, even though it does not describe individual molecular trajectories. It captures the behavior that matters at its scale. Quantum theory functions similarly. It captures fundamental behavior without insisting on deterministic detail. This perspective reduces pressure on explanation. Not every question requires an answer in the same form. Some questions are answered statistically. Others are answered structurally. Others are answered by showing why a certain type of answer is not available. Completeness in this sense includes knowing what cannot be specified. This inclusion strengthens rather than weakens understanding. It prevents theories from making claims they cannot support. It keeps descriptions aligned with evidence. In quantum science, attempts to force finality often lead to confusion. When uncertainty is treated as a problem to be eliminated, rather than a feature to be integrated, descriptions become strained. Accepting limits allows clarity to return. This acceptance also clarifies the relationship between theory and reality. A theory does not need to mirror reality in every detail to be effective. It needs to map relationships reliably. It needs to predict patterns accurately. It needs to remain consistent under test. Quantum theory meets these criteria with remarkable success. For the human mind, the idea of completeness without finality can be challenging. There is comfort in believing that all questions can eventually be closed. Quantum science suggests a different comfort. Stability does not require closure. Function does not require final answers. This idea resonates beyond physics. In many areas of life, systems work without being fully understood. Language functions without complete grammatical awareness. Bodies function without conscious control of cellular processes. Understanding is layered and partial. Physics mirrors this layered understanding. It does not seek to compress reality into a single finished picture. It builds reliable frameworks that can be extended and refined. This refinement does not indicate failure. It indicates health. A theory that can adapt without breaking is more robust than one that claims finality and resists change. For dreaming minds, this view supports a calm relationship with knowledge. The mind does not need to resolve everything before resting. Completeness does not require exhaustion. It requires coherence. Reality continues to unfold, whether or not it is fully described. Processes interact. Patterns persist. The absence of finality does not create instability. As night deepens, this understanding can feel relieving. There is no deadline for comprehension, no obligation to finish the picture. Knowledge can remain open without becoming fragile. Completeness in science is about having enough structure to move forward reliably. Finality is not required. In the next part, we will explore how these ideas influence the relationship between science and meaning, and why quantum science reshapes questions without providing metaphysical answers. As quantum science reshaped ideas about certainty, causality, and completeness, it also influenced how questions of meaning are approached, not by providing answers to those questions, but by changing the conditions under which they are asked. This distinction is important because science and meaning operate in different registers, even when they intersect. Physics does not define purpose. It does not assign intention to natural processes. It does not claim that the universe aims at outcomes. Quantum science maintains this boundary clearly. Its role is to describe behavior, not to interpret significance. At the same time, the structure revealed by quantum theory alters how humans think about meaning. When reality is no longer assumed to be rigid and fully predetermined, the space for interpretation changes. Questions shift from seeking fixed explanations to exploring relationships and constraints. This shift does not require metaphysical conclusions. It does not imply that meaning is hidden within particles or embedded in equations. It suggests that meaning is not dictated by physical structure, but neither is it contradicted by it. Quantum science shows that the universe operates through patterns that are consistent yet open. Outcomes are constrained but not fixed in advance. Processes unfold within laws that allow variation. This combination can influence how meaning is considered without defining it. Importantly, science does not compete with meaning. It limits itself intentionally. By refusing to answer questions it cannot test. Science preserves clarity. Meaning arises in contexts where values, experience, and interpretation matter. These contexts are not reducible to physics. This separation is often misunderstood. Some assume that if science does not address meaning, it negates it. Others assume that scientific discoveries must validate particular interpretations of meaning. Both views misrepresent the relationship. Quantum science neither confirms nor denies meaning. It reframes certainty. It reshapes expectations about explanation. It leaves meaning to be addressed through other forms of inquiry. This reframing can be stabilizing. It removes pressure to extract significance directly from physical laws. Meaning does not need to be encoded in equations to be real. It emerges from interaction between humans and the world they inhabit. At the same time, quantum science can influence how meaning is experienced. The recognition that reality is not fully fixed can reduce the demand for absolute narratives. It allows meaning to be approached as something that develops rather than something that must be discovered fully formed. This approach aligns with many human experiences. Meaning often emerges through context, relation, and time. It is not always present at the beginning of a process. It develops as understanding deepens. Quantum science supports this dynamic view indirectly. by showing that reality itself is relational and contextual. It encourages a view of meaning that is likewise relational. Meaning becomes something shaped by interaction rather than imposed from outside. This does not imply relativism. Constraints still exist. Just as physical outcomes are limited by law, interpretations of meaning are limited by coherence, consistency, and shared understanding. Meaning is not arbitrary. It is structured by context. The discipline of science reinforces this structure. By maintaining clear boundaries, it prevents confusion between description and interpretation. Physics describes how systems behave. Meaning arises from how humans relate to those behaviors. For dreaming minds, this distinction is essential. The aim is not to merge science with spirituality or philosophy. It is to allow science to inform reflection without turning it into doctrine. Quantum science becomes a backdrop rather than a message. It provides a landscape in which questions can be held gently without demanding resolution. This gentle holding is especially important at night. As attention softens, the need for definitive answers often decreases. Curiosity remains, but urgency fades. Science supports this by offering reliable structure without demanding belief. The universe continues to operate according to law, regardless of interpretation. Particles interact, information flows, patterns emerge. Meaning is not required for these processes to occur. Yet meaning remains important to human experience. It shapes motivation, connection, and understanding. The science does not replace it. It coexists with it. Recognizing this coexistence allows both domains to remain healthy. Science remains disciplined and grounded. Meaning remains flexible and personal without becoming unmoored. Quantum science, by softening certainty, reduces the pressure to force meaning into rigid frameworks. It allows meaning to remain responsive to experience. As the night continues, this responsiveness can feel calming. There is no need to resolve everything. There is no need to decide what the universe means. Reality behaves reliably, whether or not meaning is assigned. This perspective supports rest. The mind can release the demand for interpretation. It can allow questions to exist without answers. Science does not close them. It frames them. In the next part, we will explore how awareness fits into this picture, and why quantum science does not explain consciousness, yet still influences how consciousness relates to reality. Awareness is one of the most familiar aspects of human experience, yet it remains one of the least understood from a scientific perspective. People are aware of thoughts, sensations, memories, and perceptions, and this awareness feels immediate and undeniable. It is tempting to assume that a theory, as deep and unfamiliar as quantum science, might offer an explanation for consciousness itself. Physics does not make this claim. Quantum science does not explain awareness. It does not define consciousness. It does not identify a mechanism by which subjective experience arises. This absence is not a failure. It reflects a clear boundary between what physics is designed to describe and what belongs to other forms of inquiry. Physics describes how systems behave, how interactions unfold, and how information is constrained and transformed. Awareness involves first-person experience, meaning, and interpretation. These features are not directly accessible through measurement. Quantum theory remains silent on them by design. This silence is often misinterpreted. Some assume that because quantum science includes uncertainty and observer-related language, it must involve consciousness directly. In physics, the word observer refers to a system that interacts and records information, not to a conscious subject. Awareness is not a variable in quantum equations. Clarifying this point preserves both science and experience. It prevents physics from being asked to answer questions it cannot test, and it prevents consciousness from being reduced prematurely to physical terms that do not capture its character. At the same time, quantum science influences how awareness is situated within reality. By showing that physical description depends on interaction and context, it removes the assumption that reality is fully defined, independent of all relations. This does not elevate awareness to a causal role. It situates it within a relational world. Awareness exists within a physical environment that follows quantum laws. The brain operates through physical processes that are ultimately grounded in quantum interactions, even if those interactions average out at large scales. This grounding does not explain awareness, but it connects awareness to a lawful world. This connection is often misunderstood as reduction. Quantum science does not reduce awareness to particles or probabilities. It acknowledges that awareness arises in systems that are physical, complex, and relational. How awareness arises remains an open question. Open questions are not gaps to be filled immediately. They are boundaries that guide careful inquiry. Physics maintains such boundaries deliberately. Some researchers explore how information processing relates to consciousness. Others study how neural activity correlates with experience. These efforts belong to neuroscience and cognitive science, not to quantum mechanics directly. Quantum theory provides context, not explanation. This separation allows awareness to remain meaningful without being forced into inappropriate frameworks. It also prevents science from drifting into speculation, unsupported by evidence. From a broader perspective, quantum science indirectly affects how awareness is experienced. By softening assumptions about certainty and control, it can reduce the expectation that awareness must grasp reality completely. The mind can participate without mastering. This shift can be subtle but significant. When certainty is no longer demanded, attention can relax. Awareness does not need to fix outcomes or resolve ambiguity. It can observe patterns without insisting on closure. This does not mean awareness becomes passive. It means it becomes responsive rather than controlling. Experience unfolds within structure rather than being imposed upon it. In daily life, awareness often carries a sense of effort. The need to understand, predict, and manage can create tension. Quantum science, by demonstrating limits to certainty, legitimizes the release of that effort without undermining reliability. Reality continues to function without continuous supervision. Processes unfold, interactions occur, outcomes arise within constraints. Awareness does not need to intervene for structure to persist. This realization can be grounding. It places awareness within a larger system that does not depend on it, yet remains accessible to it. Awareness becomes a participant rather than a controller. For dreaming minds, this perspective supports rest. The mind does not need to hold explanations. It does not need to resolve how awareness fits into the universe. It can simply experience being present within a structured world. Quantum science does not diminish awareness. It leaves it intact by not overreaching. It allows awareness to remain what it is without demanding a physical explanation that may not be available. This restraint is a form of respect. It respects the limits of method and the richness of experience. As night continues, awareness can soften into observation without demand. Thoughts may appear and fade. Sensations may drift. Nothing needs to be understood fully. Reality behaves reliably. Awareness experiences it. The relationship does not need to be explained to be lived. In the next part, we will begin to draw these ideas together, moving toward a quiet synthesis that allows the journey through quantum science and reality to settle without final conclusions. After moving through uncertainty, probability, interaction, scale, and awareness, a pattern becomes visible. Quantum science does not replace everyday reality. It does not overturn experience. It quietly reframes how the structure beneath experience is understood. This reframing does not demand action. It invites perspective. The most important feature of this perspective is restraint. Quantum science does not attempt to explain everything at once. It builds reliable descriptions where they apply and accepts limits where they appear. This discipline allows complexity to exist without forcing it into a single story. Holding the whole picture does not mean assembling all details into one image. It means recognizing how different layers coexist. At human scales, objects remain stable. At small scales, probabilities govern behavior. At large scales, patterns emerge through accumulation. None of these layers contradict the others. This layered understanding allows reality to remain coherent without being rigid. Stability is real. Uncertainty is real. Each appears where it belongs. For many people, discomfort arises when these layers are confused. When quantum ideas are applied to everyday experience without accounting for scale, reality can seem unstable. When classical assumptions are applied to microscopic systems, quantum behavior can seem unreasonable. Clarity returns when each description is used appropriately. Physics operates by respecting these boundaries. It does not require a single final model that explains all phenomena simultaneously. It requires consistency across domains where descriptions overlap. They must agree where they differ. They must apply to different conditions. This approach preserves continuity. Knowledge does not reset when scale changes, it adapts. In this sense, quantum science is not disruptive. It is integrative. It extends understanding without discarding what already works. Classical mechanics remains useful. Statistical descriptions remain valid. Quantum theory adds depth rather than replacement. For the human mind, this integration can feel calming. There is no need to abandon familiar experience to accept scientific insight. The world does not become foreign. It becomes layered. Holding the whole picture also involves recognizing what is not included. Quantum science does not address values, purpose, or meaning directly. It does not explain awareness. It does not assign intention to the universe. These omissions are deliberate. By maintaining these boundaries, science avoids confusion. It allows other forms of understanding to operate without interference. Meaning can arise from experience, relationship, and reflection without needing scientific validation. This separation is not a division. It is a coordination. Science provides structure. Experience provides significance. Each remains intact. As these ideas settle, the demand for resolution begins to fade. The mind does not need to decide what reality ultimately is. It only needs to recognize how reality behaves under different conditions. This recognition is sufficient. Quantum science does not ask for belief. It asks for consistency. It does not require agreement on interpretation. It requires agreement on behavior. This modest requirement is one of its strengths. The universe continues to operate according to these principles, regardless of understanding. Particles interact. Information flows. Patterns persist. Human comprehension is not a prerequisite for order. This realization can be relieving. It places responsibility back into proportion. Reality does not depend on constant interpretation. It does not require attention to function. For dreaming minds, this proportion is essential. The aim is not to hold complexity tightly. It is to allow it to exist without pressure. As the night deepens, holding the whole picture becomes less about analysis and more about acceptance. Reality does not need to be simplified. It does not need to be resolved. It only needs to be allowed. Thoughts can drift across these ideas without settling on conclusions. Understanding can remain partial without being inadequate. Questions can remain open without creating tension. The structure revealed by quantum science supports this openness. It shows that reality itself operates without finality. Processes continue. Outcomes arise. Patterns repeat. Nothing requires closure. In the final part, we will let this understanding settle fully, allowing the journey through quantum science and reality to come to rest without answers, without urgency, and without effort. After moving through ideas of probability, interaction, scale, time, information, and limits, there is no final statement to make about reality. This is not because understanding has failed, but because understanding has reached a place where effort is no longer required. Quantum science does not conclude with a single message. It concludes with a posture, a way of holding questions without needing to resolve them, a way of trusting structure without demanding certainty, a way of recognizing reliability without insisting on control. Throughout this journey, nothing has asked for belief. There has been no instruction to accept a particular interpretation, no request to adopt a worldview, no pressure to reach agreement. What has been offered is a consistent picture of how physics approaches reality, carefully, patiently, and within limits. Those limits are not weaknesses. They are guides. They prevent overreach. They keep description aligned with evidence. They allow complexity to exist without being forced into closure. Reality, as described by modern physics, is neither rigid nor chaotic. It is structured and open. Outcomes are constrained, not predetermined. Patterns persist, even when details vary. Interaction shapes behavior without imposing intention. This structure does not need to be understood fully to function. It operates whether it is observed or not. It unfolds without supervision. It does not require interpretation to remain coherent. For the human mind, this can be freeing. There is no obligation to extract meaning from equations, no requirement to explain awareness through particles, no need to resolve uncertainty before rest becomes possible. Understanding can remain partial without being fragile. The mind often seeks final answers because it associates closure with safety. Quantum science suggests a different kind of safety. Stability can exist without finality. Reliability can exist without absolutes. Trust can exist without total control. As these ideas settle, attention naturally softens. The effort to hold everything together relaxes. Thoughts no longer need to form conclusions. They can pass without resistance. This is not disengagement. It is alignment. Alignment with a reality that does not demand mastery. Alignment with a structure that supports consistency without insisting on certainty. Alignment with a process that continues regardless of explanation. At night, this alignment becomes easier. The urgency of the day recedes. The need to decide diminishes. Awareness can remain present without effort. Quantum science does not change the night. It does not alter sleep. It does not provide instructions. It simply removes some of the weight carried by certainty. The world remains dependable. Time continues. Interaction unfolds. Patterns repeat. Nothing is required from awareness for these processes to continue. This realization allows the mind to rest without vigilance. If questions remain, they can remain. If understanding feels incomplete, it can remain. Nothing essential is missing. Nothing needs to be finished. Reality does not pause for answers. It does not wait for interpretation. It behaves according to structure, quietly and consistently. As sleep approaches, the relationship between awareness and reality can become simple. Awareness experiences. Reality unfolds. Neither needs to explain the other. There is no need to watch closely. No need to track ideas. No need to remember details. The structure described here does not depend on memory. You can let these thoughts fade without losing anything important. They are not instructions. They are not conclusions. They are context. Context that allows rest. The journey through quantum science and reality does not end with an answer. It ends with permission. Permission to stop searching. Permission to release certainty. Permission to let structure hold what does not need to be held. Nothing more is required. The night continues on its own. You can rest now,